Good morning, students. Today we are going to start a very first chapter in chemistry, which is periodic table, chapter 1. So periodic table, as you have already studied in class 9 also, that it is a tabular arrangement of elements in groups and in periods. You have already seen that there are 18 groups altogether in the periodic table and the number of periods are 7. So 18 groups and 7 periods make the periodic table. In this chapter, what we are going to mainly focus on will be the periodic properties. You can see the periodic properties are atomic size, metallic character, non-metallic character, ionization potential, electron affinity and electronegativity. So these are the various periodic properties that we'll be dealing with in this chapter. But before coming to all those periodic properties, let us see why are these called periodic properties. They are called periodic properties because they appear at regular intervals. If you remember in class 9, we saw few examples how the properties of the elements vary while moving across the period, and also we have seen that the elements in a particular group shares the similar properties. So they are called periodic properties because they appear periodically, that is after regular interval of time. And the phenomenon is called periodicity. Modern periodic law, this law was given by Henry Moseley, which formed the modern periodic table. So this law states that the physical and chemical properties of elements are the periodic functions of atomic numbers. The modern periodic table that is formed today are the elements which are arranged in the order of increasing atomic numbers. There were many scientists who created their own periodic table, but because of various reasons, those tables were discarded and a new form of periodic table was created by Henry Moseley. Now, what is the cause of periodicity? The main cause of periodicity is occurrence of similar electronic configuration. Each element has its own atomic number, from where we can find the electronic configuration, and if the electronic configuration remains the same, the elements will show the similar properties. Like in the case of group, we find all elements in that particular group having the similar electronic configuration, so they share the same properties. So let us see about number of shells. There are number of orbits around the nucleus. These number of orbits are called shells. So we can see how does the number of shell vary on moving down the group and moving across the period. On moving down the group, the number of shell will increase by 1, whereas on moving across the period, the number of shell remains same. So let us see one example where these trends can be found while moving down the group and moving across the period. So I have taken examples of group and period both. You can see group 1A first. The elements are hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. Now on the basis of atomic numbers, if you write the electronic configuration, you can come to know that the number of shell is increasing by 1. Hydrogen has 1 cell, lithium has 1, 2. There are 2 cells for lithium. Sodium has 3 cells, potassium has 4 cells, rubidium has 5 cells, and so on. So we can see here clearly that the number of shell on moving down the group increases by 1. Now coming to the period, period number 3, where the elements are sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. Now when you write the electronic configuration for all these elements, sodium has electronic configuration 281 because atomic number is 11. Magnesium is 282, atomic number is 12. Then aluminium 13, silicon 14, phosphorus 15, 16, chlorine 17, argon we have 18. Now if you write the electronic configuration, you find the number of shells remains the same. Sodium has 3 shells, magnesium has 3 shells, and so is the case with all other elements in that group. Okay, next is valency. Let us see how does the valency change on moving down the group and moving across the period. In moving down the group, the valency remains same, and in period it will first increase up to 4a and then it decreases. We have some examples. First, for example, group 1a, where you can see the valency remains same. Now for group 1a, 2 and 3a, the valency will be the valence electron. As you know, here the valence electrons you can see 1, so their valency is 1. So valency in the group remains the same. Whereas in group 7a, since this is the non-metallic group, for non-metallic group, that is group number 5a, 7, 6a, 7a, the valency can be found by subtracting the valence electron from 8. So here you can see valence electron is 7. On subtracting 8, that is 7 from 8, you are getting the valency 1. Here also you get valency 1. So in this case you can see even in this group the valency remains the same. So there is no change in the valency, whether it is a metallic group or non-metallic group, valency remains the same. Now if you come to period, I have taken example of period number 2, where these are the elements: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Lithium is coming under group 1a, beryllium comes under group 2a, and so on. Now when you write the electronic configuration, we are getting 2,1 for lithium, 2,2 for beryllium, and similarly 2,8 for neon, because the atomic number of neon is 10. Now let us find the valency and check what kind of trend does it show. So here you can see the valency for lithium is 1, for beryllium is 2, boron is 3, carbon is 4, for nitrogen, because it is non-metal, we can subtract from 8 to get 3 as the valency. Then 8 minus 6, 2. The valency for fluorine is 1, neon is 0. So when you check this, you find valency first increases till group 4a and then it is decreasing. So in period, the valency will first increase up to group 4a and then it decreases and finally it becomes 0. So we can continue the same chapter next day. Till then, thank you.